All right, this video is mostly review information, but if you don't remember, don't feel bad, just pay attention. X and Y intercepts. To find an x-intercept, the y value is 0, so you plug in 0 for y. To find a y-intercept, you plug in 0 for x. All right, find the x and y intercepts for y squared minus 3 equals x. To find the x-intercept, I will plug in 0 for y. 0 squared minus 3 is just negative 3, so x is negative 3. For intercepts, always write your answer as a point, an xy point. So our x-intercept is negative 3, comma 0. Now, y-intercept is when the x is equal to 0. I will get y by itself. Y equals plus or minus square root 3. We have two y-intercepts, so 0 root 3 and 0 negative root 3. Graphs can have different types of symmetry. You can have y-axis symmetry, where it's reflected over the y-axis, x-axis, and origin symmetry, reflection through the origin. So if you were to rotate this 180 degrees, then it would look the exact same. Graphs can be symmetric by other points and other lines, but we're just going to focus on the ones you see listed here. Formal tests for symmetry. So if you want to see if you have y-axis symmetry, remember that y-axis symmetry is called an even function, and then recall that origin symmetry is called an odd function. So the tests for that, for even functions, you replace x with negative x, and if the equation is the same as the original one you started with, then you have y-axis symmetry. For x-axis symmetry, you replace y with negative y. Now this one we've not practiced, but very similar to checking for y-axis symmetry. And then the last one, for origin symmetry, you replace x with negative x and y with negative y, and if you get the same as the original equation, then you have origin symmetry. Informal tests for symmetry would be just plugging in a number and its opposite, so 2 and negative 2, for example, and then see if you get the same y value. These informal tests are not foolproof. If you want to try them out, just make sure that if your substitution produces 0, that you try some other numbers just to make sure you're not getting anything strange. I'm going to do the formal tests. So to find the types of symmetry for this, a cubic function is what I have. A cubic function, I know from the parent graphs, looks like this, right? A cubic function, so this sort of a wave, can only have one type of symmetry if it even has symmetry, and that would be origin symmetry. A cubic function, it is possible to have origin symmetry. So that's what I want to test for. Origin symmetry, we replace x with negative x and y with negative y, and if it's the same, then we're good to go. So y will be replaced by negative y. 2 times negative x cubed minus negative x. So you've basically changed the signs of both the inputs and the outputs. Reduce from there, negative x cubed does produce a negative result, so that would be negative 2x cubed, minus negative x is plus x. We don't want it to be negative y, so we're going to divide by negative 1 on both sides. Y is equal to 2x cubed minus x. This, in fact, is the same equation we started with. So this graph does have origin symmetry. Because I know the parent graph, I don't need to test for other types of symmetry because I know that a cubic can only have one type of symmetry from the types that I'm testing for, and that would be origin. This right here is an absolute value, which is a V shape. And then subtracting 2 at the end means we went down to a vertical shift. Vertical shift, that seems like it might have y-axis symmetry. In fact, an absolute value that's facing upward can only possibly have y-axis symmetry out of the 3 types we're testing, if it even has that symmetry. So let's check it out. To test for y-axis symmetry, we replace x with negative x and see if it produces the same equation. Oh, I think it is. I think it's going to work because the absolute value of negative x is simply positive x. And yes, that is the same as the original equation. So we have y-axis symmetry. Absolute value y is equal to x. Absolute value y. In fact, if I solved for x, just out of curiosity, if I added 2 on both sides, x is equal to absolute value y plus 2. That is very similar to what we have here, except for the x's and y's were switched. So you weren't, instead of looking at an up and down absolute value, you're actually looking at a sideways absolute value. A sideways absolute value could only possibly have x-axis symmetry, if it even has symmetry of the types we are testing. So let's test it by replacing y with negative y to see if it produces an equivalent equation. And I know that if I am only changing the thing that's inside of the absolute value to negative, it's going to become positive anyways because of that absolute value. So yes, number 4 has x-axis symmetry, which also means it's not a function because it would not pass the vertical line test. So as I mentioned before, we talked about even and odd functions. An even function has y-axis symmetry, and you can test if a function is even by plugging in negative x for all your x values, and the resulting function is the same as the original function. Examples of even functions are here. As you can see, even functions often have even exponents, an even degree. And then an odd function happens when you put in a negative input and the function, the new function that you get is just the negative version of the original function. Okay, f of negative x equals negative f of x. So here are some examples. You have y equals x to the 1, a line, and you 3, 5, so it appears as though those exponents are odd, which is probably why they called it an odd function. Determine whether the following functions are even, odd, or neither, of course, is an option. So here, the biggest exponent I have is a 3, so this is only going to possibly be an odd function or neither. So f of negative x is equal to negative cubed, gives me a negative result. This is now plus x. Now, negative f of x is just changing the signs of each output. So negative f of x is negative x cubed, and then positive x. Ding, ding, ding. We have a match. F of negative x is equal to negative f of x, which means that this function is odd. What do you think this could possibly be? Odd or even or neither? Well, the exponent is even, so I'm going to test if it's an even function. And visually speaking, just looking at it, I actually know what this looks like. See if you can visualize it. G of negative x is equal to negative x squared minus 4. That becomes x squared minus 4. Ding, ding, ding. That is the original. So if you plug in negative x and you get the same as the original, then you have an even function. This one we're going to test negative x, see if it could possibly be an even function. Squaring it makes it positive, minus 2x plus 2. That's not the same as the original. So it can't be an even function. Okay? This is a parabola. A parabola cannot be an odd function. So this is neither even nor odd. Points of intersection. Method 1, remember substitution? So you can solve one of your equations for one variable and then substitute it into the other equation. Or you could solve both equations for the same variable and then make them equal to each other. Those are both types of substitution. If you're dealing with non-linear, you probably don't want to have to deal with elimination. So we're going to stick with substitution here. Without using a calculator, find all points of intersection for these graphs. I have a line and a parabola. So a line is easy to solve for y. I'm going to subtract x on both sides. So negative y equals negative x plus 1. Divide by negative 1. Y equals x minus 1. This is what I will plug into the y in this equation. X squared minus x minus 1 equals 3. I'm going to distribute and get everything to one side. So I'm solving for x. Remember, I'm finding points of intersection, so I'll still need to find y. But we'll factor this. This is minus 2 plus 1. So my x values are positive 2 and negative 1. This is when we plugged in the yellow relationship into the blue. So now we're going to plug in our results from that back into the yellow to get our y values. You have 2 minus 1 gives you a y value of 1, and then negative 1 minus 1 gives you a y value of negative 2. So your points are 2, 1, and negative 1, negative 2. Just to check if I got the right answer, I went ahead and graphed the two equations after solving the blue one for y, and visually speaking, it appears as though these are the points of intersection, but you could always test by using the intersect tool on your calculator.